Radioactive thorium-230 decays according to the formula Q is equal to Q sub 0 times 1/2 raised to the T divided by 8,000, where Q sub 0 is the initial quantity in milligrams and T is in years. A. What is the half-life of thorium-230? Well, to better understand this question, let's make a table of values to get started. Initially, when time is equal to 0, the amount of thorium-230 is Q sub 0. Let's let H denote the half-life of thorium-230. That means that after H years have gone by, there will be half of the original amount, which we can denote as 1/2 Q sub 0. After 2 half-lives have gone by, we'll have half of a half of the initial amount, which is 1/4 of the original amount. After 3 half-lives, we'll have half of a quarter, which is 1/8 of the initial amount. In order to determine the half-life, we can substitute any of these ordered pairs into the original equation. Let's go ahead and substitute the ordered pair H 1/2 Q sub 0 into the original equation. We'll substitute H for T, and we'll substitute 1/2 Q sub 0 for Q, and then solve for the half-life, which is H. The resultant equation is 1/2 Q sub 0 is equal to Q sub 0 times 1/2 to the H divided by 8,000. We want to solve this equation for H. You might be able to do it just by inspection. Think, what would you substitute for H in order to get 1/2 times Q sub 0? If you're not able to think of that value, you might proceed as follows. First of all, divide both sides by Q sub 0. The resulting equation is 1/2 is equal to 1/2 to the H divided by 8,000. Notice that both sides of the equation are exponential expressions with a base of 1/2, provided that we write 1/2 as 1/2 to the first power. In order for two exponential expressions with the same base to have the same value, their exponents must be equal to each other. So it must be the case that 1 is equal to H divided by 8,000. We just simply set the two exponents equal to each other. Finally, we need to undo dividing by 8,000, so we multiply both sides by 8,000, and we find that H is equal to 8,000. So the half-life of thorium-230 is 8,000 years. For part B, we're asked to translate the equation into the form Q is equal to Q sub 0 times A to the T. Both equations are equal to Q, so let's go ahead and set the two right-hand sides equal to each other. Q sub 0 is the initial amount, and T is the time. So all we need to do is to determine what is the value of A that causes the left-hand side of the equation to be equal to the right-hand side of the equation. Our first step might be to divide both sides by Q sub 0. A is raised to the T power, so to undo the T power, we can raise both sides to the 1 over T power. When we have a power to a power, we multiply the exponents. So in this case, we have T times 1 over T is equal to 1, and A to the first power is A. On the right-hand side, we multiply the exponents T over 8,000 times 1 over T, and we end up with 1 over 8,000. So A is equal to 1/2 raised to the 1 over 8,000 power. We can evaluate this expression on our calculator. The value is approximately 0.9999. Our last step is to substitute this value of A for A in the desired form. For part C, we're asked, what is the annual decay rate? In order to determine the annual decay rate, we can determine the decay over the first year and divide by the initial quantity. To determine the first year decay, we take the initial amount and then subtract the amount after 1 year. The initial amount is Q sub 0. In order to determine the amount after 1 year, we substitute 1 for T. Q sub 0 times 0.9999 raised to the first power is equal to 0.9999 times Q sub 0. And then we divide this entire expression by the initial quantity, which is Q sub 0. Since all the terms have Q sub 0 in them, we can use the distributive property and divide Q sub 0 into each term. Q sub 0 into Q sub 0 is 1. And Q sub 0 into the second term is just 0.9999. Therefore, the annual decay rate is about 0.0001. As a percentage, this is about 0.01%.